Swayam Prabha. Digital India. Educated India.
So anyway, so one of the things I always like to emphasize is that the notion of uniform boundedness, the way it's defined here, does not imply stability, or stability doesn't imply this in either direction. Okay, we'll talk about the linear system matter later. Okay, let's not get into that now because I want to move forward a little bit. Okay, all right. Uniform stability. The only difference, see, now that you understood stability, hopefully well enough, the other notions are relatively easier to follow actually. Yeah. So uniform stability, all you do is you change this part. The initial dependence, the initial time dependence of delta goes away. That is what is uniform stability. So whenever in all these stability notions we talk about uniformity, it is somehow uniformity with respect to time. Okay. So here all that happens is the initial time dependence vanishes. That's all. Okay. And you can of course have, so it's obviously a stronger property. Yeah, it's a stronger property. Okay, and we say that the equilibrium is unstable if it is neither stable nor uniformly stable. Okay, if you have neither of these properties, then it is unstable. Okay, so one of the first exercise that I mention here is of a van der Pol oscillator. It's one of the most popular nonlinear systems. It is being used to model biorhythms, heartbeats, and so on. How a lot of rhythmic things work. Why? Because the system exhibits something like a what is called a limit cycle behavior. Yeah, which means that the trajectories sort of get into this cyclic behavior in state space. Okay, so that is the same state is achieved after a certain time, some kind of a periodicity. Yeah, just like you have biorhythms, heartbeat, and so on. So van der Pol oscillator is a very popular system for nonlinear dynamics studies. Yeah. What I want you to do is, so this is the dynamics of the system, right? This is the actual equation of the system. What I will like you to do is, tell me something about stability, uniform stability or instability of the origin. Okay, you don't need to do any analysis. I just want you to plot it in a computer for different initial conditions, make the trajectories of the system in state space. Yeah, what does the state space mean? In this case there are two states, x and x dot, correct? So, two-dimensional system, so two states x and x dot. So I want you to plot x and x dot, x versus x dot for different initial conditions, for different mu, and just look at the plots and tell me whether it's stable or not, because all you need to do is draw epsilon ball and delta ball, right? For any epsilon ball can you get a delta ball? Okay, so all I want you to do is make plots for different initial conditions x dot. Okay, so start here and see what happens. Yeah, and for different values of mu, you can choose some range of mu. Okay, and then I just want you to comment if origin is, so I will say specifically. Yeah, notice that origin is an equilibrium, by the way. Yeah, origin means x equal to 0, x dot equal to 0. Yeah, it's an equilibrium. Yeah, because if x is 0 and x dot is 0, then x double dot is 0. It's an equilibrium, valid equilibrium. So I just want you to comment by looking at the pictures. No analysis, nothing is required. The analysis is hard because without solving it, how will you analyze? Alright. Okay, now we go to a very fun example. Okay, this is a example from Vidyasagar's book, very nicely illustrates the notions of stability and uniform stability. Okay, of course, example is not by Vidyasagar, it is in Vidyasagar's book, but it is by some other control applied mathematician, and very nice. Okay, because why is it nice? Because it's easy to solve, so you can actually look at the system solutions and get a very good feel for whether it's stable, unstable and all that. Okay, what is the system? This, very easy. X dot is 6t sin t minus twice t times x. Okay, you know that this is very easy to solve, right? Because all I have to do is take this here and integrate this right hand side with respect to time. yeah, and that is it. I mean, so the solutions actually turn out to be this guy, yeah, not difficult to see that this is the solution, because if I take derivative of this, yeah, you will get 60 sin t, and the derivative of this is 2t, correct, and then this is just the corresponding initial time terms, exact same terms with opposite sign corresponding to initial time. It is just the definite integral. Okay, everybody is clear that this solution is sort of evident, yeah, okay, excellent. And the exponential comes because you have x dot divided by x, yeah, logarithmic. So, it is a linear system, all linear systems have solutions which have exponentials, okay, nice. And this is xt0, initial condition. So, you see all our actors are in the play, yeah, you have the initial time, you have the initial state, you have time, you have the state x, basically is the solution. So, we have everything that we need here. Now, once if I fix a particular t0, so for a fixed t0, I will just denote this as some gamma, yeah, the exponential of minus 6 sin t0 plus 6 t0 cos t0 plus t0 square, I denote that as a gamma, okay, because once I fix t0, this is a constant, okay, so that I can just look at the function of time, then this is k, okay, alright, okay. First thing to note is that, so what do we have to do? We obviously have to find a, given an epsilon, find a delta, right, this is our job, yeah, this is what we are trying to do here. So, before getting to that, I want to sort of understand this function. If you look at this function, this is true for this function, that 6 sin t minus 6t cosine t minus t square has to be negative for some large time, okay. Why? Huh? T squared, quadratic dominates, yeah, everything else is linear, yeah, whatever you do it does not matter, yeah, the quadratic will dominate, yeah, the negative quadratic will start to dominate beyond a certain point, yeah. So, the plot might look something like this that you have on the left, yeah, picture looks something like this. So, the good thing is, it's a, first of all, it's a nice smooth function, first of all, yeah, smooth, continuous, everything, right, this function inside the exponential is smooth, yeah, very good function, right. So, it is smoothly changing, so it is not like suddenly it can have a jump and go to infinity and come back or do something funny like that, no, right. So, it is a nice function, and I know that it becomes negative after a certain point, even if it started positive, alright. So, I am guaranteed to have an upper bound m to this function, okay, and this upper bound will be between initial time and this finite capital T, make sense, yes, yeah, just look at the picture, this picture is very illustrative of this. I mean, again, picture, the real plot may be different, there may be oscillations and all that, given that there is sinusoids, but more or less the idea is if the function is going to hit a negative value beyond a certain point, so it is going to become negative beyond this point, here it can only have limited exploration, right, by smoothness of functions and what is it, central value theorem and all that stuff, yeah, by all the nice results that you have for smooth functions. If it is positive for only a finite time, it can only have finite exploration on the y axis, can't just go to infinity and come back, okay, excellent, great. So, what is this? I define m as exactly this, the supremum from between this time of this function, okay, which is finite by continuity, okay. So, continuity smoothness gives us all these very nice results, yeah, I do not have to bang my head. So, if you give me an epsilon, what will I choose my delta as? I will choose my delta as epsilon over gamma e to the power m. Why? We will see very shortly, yeah. Remember this, I choose delta as epsilon over gamma e to the power m. So, I have repeated this here, but remember, keep this in your mind that gamma depends on T0. You ask me how the delta depends on T0 happens, right? Okay, I did not say how, why? My equilibrium is 0 in this case, So, if my x0 is less than equal to delta, which is equal to epsilon over gamma e to the power m, correct? By this expression of the solution, I know that xt is less than equal to norm x0 gamma e to the power m. Yeah, everybody gets this, understands this, right? Why? x0 is, I am just breaking it into norms, therefore there I get a less than equal to, right? First I have the absolute value here, and then when I take the separate pieces, then it becomes a less than equal to anyway, right? Just by breaking the absolute value. I am just writing it as norm to be general. I know that this is x0, I retain it as such. This is gamma, retain it as such. This is exponential of this guy, but the largest value this guy can take is e to the power m. Yeah. So, just plug in for delta here. What happens? Less than xt is less than equal to epsilon, correct? If you plug in for this delta, in fact this guy goes here, gamma e to the power m cancels. So, I just have xt is less than equal to epsilon. Yeah. So, I just proved it, proved whatever I needed, that I wanted the states to remain inside the epsilon ball. Yeah. But notice very carefully that my delta depends on the initial time, very important, delta depends on my initial time, I can't change that. So, all I have proven is stability in the sense of Lyapunov, not uniform stability in the sense of Lyapunov, okay, because my delta depends on initial time, okay. Also remember that it depends on epsilon also, that is what the picture I kept making, right. You give me a small epsilon ball, I will give you a small delta. If you give me a large epsilon ball, I will give you a large delta, right. So, delta will sort of scale, in fact linearly with epsilon in this particular case, it will scale linearly, okay, you can't ignore this, yeah. So, not guaranteeing any boundedness, okay, great. So, everybody is, I hope, convinced that this is stable. What about uniform stability? Now, I want this delta to make this delta independent of T0. So, that is the question I ask here. Can gamma be independent of T0? Because that is the only T0 dependence, right? Nothing else depends on T0, only gamma. So, if I want to make delta independent of T0, I need to look for ways to make gamma independent of T0, okay. Now, the important thing to understand is whenever I am trying to find a common delta that is independent of T0, I have to hunt for the smallest delta. I hope this is sort of evident, okay. For example, I mean, I will just try to make a picture. So, suppose I give you this epsilon ball, okay, and then I give you some initial time. Corresponding to that, I give you a T0, and corresponding to that I have a delta ball. I would say this is delta ball, okay. Now, if I give you another initial time T0 prime, then I get a delta prime ball, right. Corresponding to different initial conditions, I get different delta balls. Now, the point is, if I want a delta ball which works for both initial times, for T0 and T0 prime, which ball will I choose? The smaller one, right, obviously, right, because I want to stay inside epsilon. So, it has to work for both times T0 and T0 prime, I have to choose the smaller ball. If I choose the larger ball, it will work for T0, but if I start at T0 prime, I am guaranteed to get out, or there is a potential that I get out of it, not guaranteed, but there is a potential that I escape, okay. So, I have to choose the smaller ball. So, if I extend this to all possible initial times, I have to find the smallest delta, always. If I want to get uniformity, must find the smallest delta, Okay, so that is what is mentioned here. Okay, so I want to find the smallest possible delta, which means I want to find the largest possible gamma in this case, right. Okay, now look at the expression for gamma. I have just copied it for your benefit here. What do you see? And it is written here, but it is evident that it has the opposite behavior of the t expression, right. So, this actually blows up, goes to infinity. In fact, it will become positive after a certain time, certain t0, and it will blow off to infinity because t0 square will dominate everything. Yeah. So, gamma t0 goes to infinity as t0 goes to infinity. So, there is no upper bound on gamma at all, there is no largest gamma. Yeah. Because if I choose gamma t0 as infinity, then my delta is 0, so which is not allowed, right. Delta has to be positive. Basically, you are giving no initial condition, right. So, therefore, no uniformity is possible in this case. Okay. No uniformity is possible in this case because gamma is going to blow up, alright, and therefore, it will not be uniformly stable. You cannot achieve uniform stability in this case. Okay. So, that is really the point. So, the system is stable, but not uniformly stable. Okay. So, this is how you analyze these properties. We will talk about other properties in the upcoming class, but this is sort of how you analyze the properties. You have to actually solve the system. Yeah. You can imagine that this is not realistic. Yeah. This is a very simple linear scalar system that I gave you, and we did this bunch of pretty lengthy analysis to figure all this out. Once we solve the system, yeah, you cannot expect that we are going to be able to solve most nonlinear systems. Yeah, once I give you a vector system, you will, even a second order system, you will struggle, yeah, to get an analytical solution, and any numerical answer is no answer. Yeah, do not try to ever give me numerical answers that I tried 100 initial conditions and I got that this delta works. Impossible, not acceptable. Yeah, because there may be that 101th example initial condition for which it will not work. Okay. So, numerical answers not okay, which is why subsequently, not in the next lecture, but subsequently we talk about the Lyapunov theorems, which are actually better tests. They are tests rather than, just like you have convergence tests, Lyapunov theorems are tests. Yeah, they are meant to give you easy conditions for doing this. Okay. So, not actually use these definitions, which is virtually impossible. Okay, just like the supremum definition, cannot use it. Yeah, I mean, you can't just keep scanning to find supremum of a matrix. So, you have those simple formulae. Here you have these Lyapunov theorems, okay, which will form the basis of everything we do in terms of design. Okay.